All right, so moving on from last week doing probability, we're going to look at something called compound probability. Now, that might sound intimidating, but really all that means is we're going to do more than one thing. We might pull a marble out of a bag and then pull another marble out of a bag. We're doing two separate events. Flipping a coin and then flipping a coin again, two separate events. And how does that affect the overall outcome chances of our thing here? Um, Before we get into that, this word right here is kind of important. Independent events. What that means is when I flip that coin and get a head, that does not at all affect what happens the second time. They're independent of each other. Um, Reaching in and pulling a marble out of a bag, if I put it back when I reach in the second time, the first marble has no impact on the second one. Okay, so they're independent of each other. Just keep that in mind because we will do something called dependent events, and that's a whole separate lesson. But what happens the first time does affect what happens the second time, and I'll explain that more when we get into it. But just keep that in mind. We're doing two separate things that don't affect each other. So, same thing I said last week. The notation's kind of weird on this. So if you just kind of hang through the notation, the math makes a whole lot more sense once you get into it. So the way these things are written. Okay, you're going to have the same big P for probability, and then in the parentheses, you're going to have two separate events. So the examples that I have here, we're going to, flip a coin and get a head, and then flip a coin and get another head. So it might say, probability head and head, something like that. The way this works out, you treat those events separately. You find the probability of the first one and the probability of the second one, and then you just multiply them together. If you're not real comfortable with fractions, the multiplication might be a little bit intimidating, but I'll try and walk you through it and give you a little refresher on that. So we're going to flip a coin here. Actually, we're going to flip two coins, one in each hand, and we're going to see what the chances are, what the probability is that they both land on a head, right? They both land heads up. Well, from what we did last week, there's one head that we want. There's two possible outcomes on the coin. So the probability that we get a head is 1/2, and then I'm going to flip a second coin, same probability of 1/2. Now, two separate events, so I have two separate probabilities. To get that compound probability, I'm going to multiply those together. To multiply fractions, you just go straight across. Numerator times numerator is 1. Denominator times denominator is 4. Okay, so I kind of think it's worth explaining what's actually going on here. If you consider, like, we've got two separate coins here, all of the different outcomes that could happen. That first coin could give us a head, that second coin could give us a head. The first coin could give us a head, the second one could give us a tail. Then we could get a tail here and a tail here, or we could get a tail here and a head here. With a coin, since there's only two possible outcomes, it's really easy to list everything. Deck of cards is a completely different ballgame, but if you flip two coins, there's only 4 possible outcomes ever, and we're just trying to see how many of them are actually what we want. All right, rolling 2 dice. This is not rolling a pair of dice in a game, but it is similar. So we're going to roll a single die, right? And I want to know the probability that we can get a 6 when we do that. And then I'm going to pick that dice up and I'm going to roll it again. So that's another probability of 1/6. So that overall compound probability is 1 out of 36. If you go back and look at that table from last Thursday that had all the different possibilities for throwing a pair of dice, there's 112, which would be 2 6s out of that whole table too. So it's kind of similar. All right. Those are like the two most basic examples I could come up with. This one with the marbles gets a little more complex just because there's more marbles. There's literally more things going on here. So we're going to reach into this bag, which, by the way, there are 20 marbles in this bag. Okay, so when we set these up, our probability here is going to be out of 20, and then our probability here is going to be out of 20. I don't know why I wrote 12. Just thinking ahead. 20 and 20. So the numerators, I want to know the probability that I can reach in here and pull out a blue. That's going to be 6/20ths. And then the probability I could pull out a red is going to be 9/20ths. Now you can multiply these straight across and get 54 out of 400, but you're going to have to reduce that. I think it's a little bit easier if you stop before you multiply and take a look at your fractions here. I'm going to reduce down 6/20ths to 3/10, and then 9/20ths doesn't reduce. So now I'm multiplying 3/10 and 9/20ths. I can get 27/200ths. A little bit easier to reduce if you do it when the numbers are smaller than when they're bigger. If you're not using a calculator, if you're using a calculator, you can just do it at the end and kind of make it a little bit easier on yourself. So a red than a red, that's 9/20ths and 9/20ths again, since it's the same color marble. If I'd switch colors, that'd be a different fraction for the second one. So that's 81/400ths. That doesn't reduce because neither one of these guys reduced before we multiply. So the product at the end isn't going to reduce either. Not blue, 14/20ths, and then a blue, 6/20ths. These you can reduce. That's going to be 7/10ths, and this guy will be 3/10ths. So when I multiply, it's 21/100ths. That means that there is a 21% chance that I can get a not blue marble, put it back, and then draw out a blue marble.